Welcome to this lecture. We shall now begin our three-part discussion of the life history of stars. It turns out that the life history of stars depends upon their masses. In today's lecture, we shall discuss the evolution of low-mass stars such as our own Sun. The first concept I want to introduce to you is what is known as the zero-age main sequence of stars. I shall explain what this is by showing you this diagram, which is perhaps the most important diagram in stellar astronomy, and it goes by the name of Hertzsprung-Russell diagram, named after two most distinguished astronomers. Now let me explain the axes. What is plotted on the y-axis, I am showing you the right side of the y-axis, is the luminosity of the star increasing as we go up. What is plotted on the x-axis is the temperature or the surface temperature of the star as we go from right to left. It's a strange convention that astronomers have adopted. Now what is shown in this plot are the locations of stars for which distances and therefore luminosities and surface temperatures have been determined from observations. You clearly see that there are many special features of this. This central diagonal band of stars, where most of the stars are, is known as the main sequence of stars. Then over here, you have giant stars whose radii are very large. And then above that, you have supergiants whose radii are even larger. Down in the left-hand bottom corner, you have dwarf stars, which are known as white dwarfs. We shall discuss all of these in the coming lectures. Now here is my version of the zero-age main sequence. Luminosity of the star increasing vertically, and the surface temperature of the star increasing as I go from right to left. The low-mass stars are in the bottom right-hand side over here. Solar mass stars are over there where the cursor is at the moment. These are the intermediate mass stars with masses between 2 and roughly 9 or 10 solar masses, and these are the massive stars. Today's lecture we shall be concerned with the evolution of low-mass stars. But before we proceed, let me say a few words about the significance of the main sequence. All stars in the main sequence are converting hydrogen to helium at their centers. I should also add that all stars spend most of their lifetimes in the main sequence. And the other acts of the stellar drama, as we shall see, are very short-lived. So the two things that you must remember is that most of the stars spend almost their entire life on this diagonal main sequence, and all stars on the main sequence are converting hydrogen to helium at their centers. Now, the result of this hydrogen fusion, or hydrogen burning as it is loosely called, is a helium core, and I shall argue that the helium core will be inert. In other words, it is not producing energy by fusing helium into heavier elements. At some stage, helium will fuse to form carbon, and then carbon will fuse to form heavier elements and so on. So the idea of the nuclear cycle is that the byproduct of one stage of fusion reaction should serve as the fuel for the next stage of nuclear reactions. Now let us consider the stellar drama. The stellar drama is a many-act play. Now the question is, why is the story of the evolution of stars not a one-act play? Why are there many acts? And the reason for this is something that I have already explained in an earlier lecture when we discussed energy production in the stars. What is shown here is the potential energy diagram. In potential energy, the vertical direction, and the distance between two nuclei in the horizontal axis over there. So, when two nuclei approach one another, they repel each other due to Coulomb repulsion. And that Coulomb energy is indicated by this dash curve. This is the Coulomb barrier. The height of the Coulomb barrier depends upon the charges of the two nuclei. If the two nuclei have charges 1 and 1, namely two protons colliding against each other, the height of this potential barrier is 1 million electron volt. In general, it is Z1 into Z2 million electron volts, where Z1 and Z2 are the charges of the two colliding nuclei. I already explained to you that if the central temperature of the star is 10 million degrees, say, that corresponds to an average energy of the particles of roughly 1,000 electron volts, which is over there, E1. Therefore, if two protons with the average energy of 1,000 electron volts approach one another, then they will run into this potential barrier, and they cannot overcome this barrier and come close enough to fall into this attractive nuclear potential well. So we invoked the idea of quantum mechanical tunneling. So the proton tunnels through this potential barrier, an idea which was first introduced by the Russian physicist George Gamow. Now, down below on the right-hand side, I've written the expression for the tunneling probability or the transparency. And I stress in the earlier lecture that this tunneling probability is an exponential function, and it depends upon the height of the potential barrier, it depends upon the energy of the particle, and it depends on the mass of the particle, and it also depends upon the width of the potential barrier. If the width of the potential barrier is large, then the tunneling probability will be exponentially small. Similarly, if the energy of the particle is small compared to the height of the potential barrier, V minus x will be large, and the tunneling probability will be exponentially small. But we know fusion reaction does take place in the center of the sun, and hydrogen is being converted to helium. And 100 years later, after the conjecture was made, we certainly have final proof. The smoking gun has been found. Now the question is, will heavier nuclei also fuse? Now, if two helium nuclei, for example, have to fuse, then the height of the potential barrier will be 4 times larger. Z1 is 2, Z2 is 2. Therefore, if the central temperature is still the same, and if the average energy of the particle is still E1, then the particle will have to tunnel through a very wide potential barrier, and the tunneling probability down here will be practically 0. How to overcome this? Well, if the temperature in the central region is now higher, and therefore the mean energy of the particle is higher, then the particle would have to tunnel through a smaller potential barrier, and therefore fusion reaction can take place. Therefore, the moral of the story is, to fuse heavier nuclei, one has to overcome a higher potential barrier, and to have a significant tunneling probability, the colliding nuclei have to have higher energy, and this in turn means higher central temperatures. As I explained to you in the earlier lecture, hydrogen will fuse to helium comfortably at a temperature of 10 million degrees. But in order to fuse helium to form carbon and a little bit of oxygen, you need a temperature of 100 million degrees. And to fuse carbon, you need a temperature of 500 billion Kelvin. And to fuse oxygen to form silicon, etc., you need a temperature of 1 billion degrees, and so on. So, the fusion reaction are extremely sensitive to the temperature. So the fusion reaction proceeds in the following fashion. There is a certain reaction. It produces an inert core, and that inert core is contracted by gravity, and this contraction leads to heating, and this heating leads to further fusion reaction, and this nuclear cycle will go on. These are the various acts of the stellar drama, if you like. The ultimate goal of fusion reaction is to start with hydrogen and end up with iron 56, which is the most tightly bound nucleus, because the binding energy per nucleon is the largest for iron 56 nuclei. So let's assume that the stellar drama has gone on one act to the next act, to the next act, till the final act. And suppose you're Superman and went into the star and looked right at the center of the star. What will you find? You'll find this. You'll find right at the center an iron core, and in the outer boundary of the iron core, silicon will still be being converted to iron, and then you'll find a layer where the oxygen is being converted to silicon, and then you'll find a layer where neon is being converted to oxygen and magnesium, and then a layer where carbon is being converted to neon and magnesium, and then you have a layer where helium is being converted to carbon, and then hydrogen being converted to helium. This is all right at the central region of the star, and out there is the rest of the star, millions and millions of kilometers in radius. So the core of the star at the end of the stellar drama will look like an onion with many, many, many layers. This is known as the onion skin model of a massive star. To burn or not to burn, that is the question. Whether or not the nuclear reaction proceeds to the next stage depends upon whether the contracting core heats up to the required temperature that I mentioned in the earlier slide. This in turn, whether or not the contracting core heats up to the required temperature or not, will depend upon whether the core obeys ideal gas law, Boyle's law, or obeys Fermi-Dirac statistics, which we discussed at great length in the previous lecture. And this is the reason why we discussed Fermi-Dirac statistics in the previous lecture. A gas can be considered ideal if the kinetic energy of the particles is much larger than the potential energy of interaction between two particles. In classical physics, such an ideal gas obeys Boyle's law. According to Boyle's law, the pressure is given by the simple expression N times Boltzmann's constant multiplied by the temperature, where N is the number of particles per unit volume. And therefore the pressure is proportional both to the density, number density or mass density, they can be converted one to another, as well as the temperature. And the average kinetic energy of the particle of a gas at a temperature T is of course given by 3/2 kBT. If on the other hand, the gas obeys Fermi-Dirac statistics and is degenerate in the sense that I explained in the previous lecture, what will be the situation? Let me remind you once again that particles such as electrons, neutrons, protons, etc. obey Fermi-Dirac statistics. As one compresses a gas of electrons, the kinetic energy of the electron will increase because of Heisenberg's uncertainty principle. This is a direct consequence of Heisenberg's uncertainty principle, which says that delta P into delta X must be greater than Planck's constant divided by 2. Now, this motion, kinetic motion of the particles, when I compress it, has nothing whatsoever to do with heat or temperature. Electrons, protons and neutrons also have to obey Pauli's exclusion principle, which states that you can only put one particle in one quantum state. You could put two electrons in a quantum state, provided you put their spin angular momentum in anti-parallel directions, because then they would not be in the same quantum state. Now, this is how we populate a gas of electrons at the absolute zero of temperature. Imagine that you have n electrons in volume V. The energy levels are discrete in quantum mechanics. So what you do is you start putting two electrons in the ground state, making sure that their spin angular momentum are oriented in anti-parallel direction, then two electrons in the second level, two electrons in the third level, and so on, till you run out of electrons. Therefore, an electron gas, even at absolute zero of temperature, has energy, and it has an enormous amount of energy. Where does this zero-point energy come from? It comes from Heisenberg's uncertainty principle and from Pauli's principle, which says you can't put all the particles in the ground state. You can only put two particles over there. It is Pauli's exclusion principle that forces you to put particles in higher and higher energy levels, thereby increasing the total energy of the electron gas. So we said in the previous lecture that there is an energy known as the Fermi energy, which is a measure of the characteristic energy of the particle in quantum statistical mechanics. Well, particles have all energies from 0 up to EF, but the typical energy is some fraction of EF. It may be 3/5 EF, 1/2 EF, 2/3 EF, but it doesn't matter. It's of the order of EF. Now let us say that I compress the gas and increase its number density. Then what we said was that the maximum occupied level, which is the Fermi level, this Fermi energy will increase dramatically because the Fermi energy is proportional to density to the power 2/3. So, if I compress a gas, Fermi energy will go up. The significance of Fermi energy is all states up to there are occupied at absolute zero, and all states above that are unoccupied at absolute zero of temperature. Now, how to tell whether a gas obeys gas has to be described by classical statistical mechanics or quantum statistical mechanics. The characteristic energy in classical physics is kT. The characteristic energy in Fermi-Dirac statistics is the Fermi energy EF. If the thermal energy kT is much larger than the Fermi energy, then the gas will obey the classical equation of state, namely Boyle's law, if the gas is ideal. On the other hand, if the Fermi energy is much larger than kT, then the gas will obey Fermi-Dirac statistics or quantum statistical distribution. Where does this transition from classical behavior to quantum behavior occur? Obviously, when the Fermi energy and kT are approximately equal to one another. So this is where the transition occurs, and this boundary is going to play a very important role in our discussion presently. So this is the nuclear cycle that I referred to earlier, and let us proceed now. Let us say that the result of one nuclear fusion of some nucleus, let us say hydrogen to helium, produces a helium core. Now the helium core is at a temperature of 100 million degrees. Therefore, helium cannot fuse to form carbon. It needs a temperature of 100 million Kelvin. So what happens in the meantime? There is no pressure generated inside the core. Remember our equation of hydrostatic equilibrium? dP/dr is equal to minus Gm rho by r squared. If there is no energy being generated in the core, then gravity will become stronger in comparison to when the core was generating energy, and therefore gravity will try to squeeze the core to a smaller radius. Now let us examine what will happen to such a contracting core. Let us first consider the case where the gas in the core is classical and obeys Boyle's law. Now as the core contracts, it will heat up. Why will it heat up? Because in an adiabatic compression, this is the relation between temperature and density. I'm sure you've heard of adiabatic processes in which the entropy remains constant. There is no heat exchange with the outside world. In such a compression, there are some well-known relations. For example, PV to the power gamma is a constant. From that, I can write T rho to the power 1 minus gamma is a constant. What is gamma? Gamma is the ratio of specific heat of the gas at constant pressure divided by the specific heat at constant volume. For an ideal gas, gamma is 5/3. I refer you to any elementary book on thermodynamics, and there you will read about these adiabatic relations and the value of gamma being 5/3. So the moral of the story is, if the gas is classical and if I compress it, it will heat up as a consequence of this adiabatic relation. Now let us consider a quantum core. As the core contracts, there will be no heating. As the core contracts, the density of electrons will increase, and therefore the pressure of the electrons will increase. But the pressure of an electron gas, a degenerate electron gas, has nothing whatsoever to do with the temperature. That pressure arises by virtue of Heisenberg's uncertainty principle and Pauli's exclusion principle. Therefore, pressure and temperature are decoupled in the quantum core. Therefore, you can see that this stellar drama, the second act of the stellar drama, depends on whether the contracting core obeys classical equation of state or Fermi-Dirac equation of state. Now, whether the stellar drama will play out to the last act or not, the last act is when it has produced iron 56 and the fusion reaction ends there and the core will look like an onion. It will depend upon whether the contracting inert core becomes degenerate or not. If the contracting core remains classical through all the acts of the stellar drama, curtain going up and coming down, then the stellar drama will proceed all the way till iron 56 is produced. But on the other hand, if the star was unfortunate enough to form a degenerate core in the center, then the situation is very different. And that's exactly what happens in low mass stars and intermediate mass stars, and the core will become degenerate as it contracts. Whereas in massive stars, it will remain an ideal gas. Therefore, you can already tell from here that the life history of low mass and intermediate mass stars will be essentially different from the life history of massive stars, which remains classical through the various acts of the stellar drama. Now let us look at this plot very briefly. This will become clearer at the end of the third lecture. But let's have a preview in any case. What is plotted on the y-axis is the temperature of the gas increasing upward in logarithmic units, log T. What is plotted on the x-axis is the density of the gas increasing towards the right, again in logarithmic units. So it is log T versus log rho. Down at the center, there is this diagonal rectangular box. This rectangular box delineates classical gas behavior, which is on the left, from quantum gas behavior, which is on the right. So if the gas were at temperature and density over there, it will be classical, whereas if its temperature and density would make it over there, then it will be degenerate. Well, it could be either non-relativistically degenerate or relativistically degenerate, depending upon the density. As the density increases, Heisenberg's uncertainty principle says that the momentum will increase, and therefore at some stage, momentum will become comparable to m times c, where c is the speed of light, and then special relativity will come in. But let's not worry about that at the present moment. So as I heat this gas, as I increase the density of this gas, it will heat up but remain classical. At some stage, it will become degenerate. Now, if I were dealing with a gas at a higher temperature, and if I increase its density, then it will remain classical up to there, and then it will become quantum mechanical. On the other hand, if the gas were at this point, and if I increase the density, then it will remain classical no matter how high the density will become. Why is this slope 1 by 3? That comes from the adiabatic relation. T into rho times 1 minus gamma is a constant, will tell you that the relation between log T and log rho will be 1 by 3. Now let us come back to the evolution of low mass stars with this background in mind. So that background was a summary, in a sense, of stellar evolution and what governs stellar evolution. Now let us concentrate on the low mass stars on the right-hand side bottom over there. For example, the star like the Sun, or even lower mass star. Now near the center, like in all the stars in the main sequence, hydrogen is being fused into helium. Over a time, a helium core will develop at the center. Right now, such a core is developing at the center of our own Sun. This helium core will be inert because it has not attained the temperature of 100 million degrees, which is needed to fuse helium to form carbon. Since there is no energy generation in the core, equation of hydrostatic equilibrium will now be upset because the core is inert, and therefore gravity will squeeze the core and the core will contract. This compression will make the helium core degenerate, obeying Fermi-Dirac statistics. How do I know? Because I asked you to do a little problem in the previous lecture. Consider the density of the center of the Sun, roughly 150 grams per cubic centimeter. It's all hydrogen. So you know how many electrons are there. And its temperature is 15 million degrees at the center. I asked you to calculate kT and also the Fermi energy, which is proportional to density to the power 2 by 3. And I asked you to convince yourself that the gas will be classical because kT will be larger than EF. But when I now compress the helium core, Fermi energy increases as density to the power 2 by 3. Sure, the temperature may also increase marginally, but the increase in the Fermi energy is very dramatic. Therefore, from kT being greater than EF, kT will become less than EF, and therefore the inert helium core, upon compression, will become degenerate and will obey Fermi-Dirac statistics. Since there is no energy generation in the helium core, it will contract. The gravitational energy release will cause the envelope of the star to expand, and the star will become a giant. Let's try to understand this. What I have said is, as the core contracts, the rest of the star will expand dramatically. Why is that? This is known as Gravo-Thermal Catastrophe. Let us consider this star, which is hydrogen. This is not to scale. The star is 1,000,000 kilometers in radius, and this is the helium core that has been formed right in the center of the Sun. Gravity is squeezing this helium core. It is contracting. And the core contraction will lead to the expansion of the star. Why? As the core contracts, as I explained in the earlier lecture, the gravitational binding energy, which is minus gm squared divided by r, gravitational binding energy will be released, and you are releasing positive energy, and this positive energy will go to overcome gravity in the outer layers of the star, and the star will expand. I hope that's very clear to you. So if the core contracts, the envelope will expand. If the core expands, envelope will contract. Okay? It has to do with whether the binding energy released is positive or negative. So I hope it's very clear to you. The reason why the star expands is because when I compress the core, gravitational binding energy, potential energy is being released. And this potential energy that is being released goes to expand the outer layers against gravity. Now, so let me say this once again. There is a contracting helium core. How did this helium form? By fusing hydrogen to helium over millions and millions or billions of years. The sun has been shining for 5 billion years. It's been converting hydrogen to helium for 5 billion years. So at some stage, a substantial helium core will form, and that core will be inert, and therefore it will contract. And the contraction of the helium core, well, around the helium core, there is hydrogen, rest of the star is hydrogen. Around the helium core, the temperature is high enough to convert hydrogen to helium. So hydrogen is being continually converted to helium, even as the mass of the inert helium core increases. Now, this leads to an expansion of the star, and the size of the helium core is indicated there. Its mass is roughly 0.45 solar mass. Its radius is 1/100th of the solar radius, so it's only as big as the Earth over there. And what is there right at the center? A degenerate helium core. So a degenerate helium core contracts, inert helium core contracts, becomes degenerate. During the contraction, gravitational binding energy is released, which expands the rest of the star. And there is still hydrogen being converted to helium over there. The star will now have a very large radius of almost 50 times the present radius of the sun. So its radius will become from 1 million kilometers to 50 million kilometers. It will be a red giant star. The star will also become convective when it suddenly expands. I do not have time in this lecture to explain why convection sets in. It's extremely important phenomena, but perhaps in one of the later lectures we shall digress for a few minutes to understand why suddenly convection occurs. Very briefly, convection occurs when the temperature gradient increases above a critical value. If you have a pot of water and you put it on your stove in your kitchen and you heat it, initially the vessel gets hot and the water at the bottom gets hot, and that heat is transmitted upwards by convection. But when the temperature gradient, there is a temperature gradient between the bottom of the pan and the water at the top of the pan, the upper level of the water, and when that temperature gradient exceeds a critical value, water becomes turbulent, and you can see bubbles rising and sinking, and this is the phenomena of convection. Same thing happens in a star. Now, let us see this let's go back to the Hertzsprung-Russell diagram, where we have plotted the luminosity increasing vertically in the y-axis, the surface temperature increasing as I go from right to left. This is the main sequence of stars. Let us say we are considering a star of 1 solar mass like the sun. Now, let us say in this picture how the evolution will be. So, the star will become a giant. Remember, I had plotted lines of constant radii. So this is 1 solar radius, this is 10 solar radii, this is 1/10th of the solar radius, 1/100th of a solar radius, and so on. So quite clearly, the location of the star will go from here to there. Over here, there is a, why doesn't it go like that? That's a very interesting region. There is a forbidden region here, which is defined by an almost vertical line, which is known as the Hayashi line, named after a famous Japanese astrophysicist, Hayashi. And over here, the star will become mechanically unstable, and therefore you cannot have a stable star in this condition, in this to the right of this dashed red line. So now you have a red giant, and what do observations tell you? Here, this is the Hertzsprung-Russell diagram, luminosity versus temperature, of not some hypothetical theoretical plot, but an actual plot of almost 1 million stars, whose distances and luminosities have been measured by this remarkable satellite Hipparcos, which was launched about 10 or 15 years ago. Hipparcos' main objective was to measure distances to stars, and this is what you find. So you find very clearly that there is a main sequence of stars where the majority of stars are, and then you have the stars going in this direction towards red giant. There's a traffic jam over there, and that's where they end up. So that's it. Now let's go back to the contracting helium core. It is true that because the helium core is degenerate, as I compress it, it doesn't get hotter. But please remember, you're trying to bake a pizza in an oven. You have run out of firewood inside the oven, therefore the pizza will not bake. But please remember that the outer wall of the oven or your tandoor is still extremely hot. Why? Because outside the outer wall, hydrogen is still being converted to helium. So there is a furnace outside which is still burning, hydrogen being converted to helium. That heat will conduct inwards, and therefore the inert helium core will get hotter, even though that heating is not by virtue of compression. It is not by virtue of compression because it obeys Fermi-Dirac statistic, but it is being heated externally, if you like, by the outside furnace. And eventually, when the temperature of the core reaches 100 million degrees, helium will fuse to form carbon. And detailed computer calculations show that helium will ignite to form carbon when the mass of the helium core reaches roughly half a solar mass, regardless of whether I'm dealing with a 1 solar mass star or a 2 solar mass star or a 0.75 solar mass star. When the helium ignites, the star is in a serious predicament. Why? So here is a star. This is again log temperature versus log density plot. The helium core the density was increasing. It remained classical, but then it crossed the danger line and it became quantum mechanical, which is to the right of this dashed line. And there, at that density and temperature, helium ignites to form carbon, and all hell breaks loose. Why? Let's remind ourselves of something that I said much earlier. You have a helium core at a certain temperature and a certain pressure. For some reason, the luminosity increases. Why? Because the temperature needed to ignite helium has been attained, 100 million degrees. Therefore, the luminosity increases, therefore the temperature will increase. Therefore, the core will get hotter. But because the core is degenerate, it will get hotter all right, but its pressure will not increase because pressure of a degenerate Fermi gas has nothing whatsoever to do with temperature. So it will generate more energy now, because please remember, the hotter it is, the higher is the average energy of the particle, and the tunneling probability for fusion reaction will increase exponentially with increasing energy of the particle. Therefore, there will be an even larger increase in the luminosity and the core will get even hotter, but the pressure will still remain the same. And then it will get even hotter. The pressure will remain the same. It will get even hotter and hotter and hotter till finally the star will blow itself apart. So, let me repeat once again. In a degenerate gas, the pressure is decoupled from temperature. So the pressure remains the same, but the temperature continues to increase. As the temperature increases, the fusion reaction proceeds more furiously, and so much energy is released that gravity is completely overcome and the star will blow itself up. So will the sun blow itself up? Well, it will try to, but it won't succeed. Why? Well, when helium ignites, there is a runaway fusion reaction and the luminosity generated in the core will become million times larger than what it was before. But before the star itself blows itself up, the safety valve that I had talked about in the lecture on energy production will come into operation. Why will the safety valve suddenly become operational? Because as the core gets hotter, kT will creep up in relation to the Fermi energy. At some point, kT will become comparable to the Fermi energy, and eventually kT will become larger than the Fermi energy, and the gas will no longer be degenerate, and therefore the gas will expand and cool and bring down the chaos. Therefore, the helium bomb will be like your Diwali cracker. You think it's going to go off, but then it's a dud. It doesn't really go off. So let's try to understand once again how the safety valve works. There is a core at a certain temperature and pressure, and the gas obeys Boyle's law. For some reason, there is an increase in energy production that heats up the core gets hotter. Because the gas obeys Boyle's law, as the core gets hotter, the pressure will also increase because the pressure is nKT. As the temperature increases, the pressure will increase. So the pressure will go from P to P plus delta P. And this will upset the hydrostatic equilibrium. The core will now expand. As the core expands, the core will cool. And as the core cools, the energy production will decrease and it will come back to where it started. So if you play some mischief with an ordinary ideal gas core, then the mischief is undone by this safety valve. But if the core is degenerate, there is no safety valve and the star will blow itself apart. So let's now go back to the Gravo-Thermal Catastrophe. We said the core will expand. What will the star do as the core expands? As I said, when the core contracts, star will expand. When the core expands, the star will contract. Okay? Why? Because of the dependence of the gravitational potential energy on the radius. Gravitational potential energy of mass m and radius r is minus g m squared divided by r. So, soon after, so here you had the red giant star. Soon after the helium ignites in the core will expand in response to the heat generated. The expansion of the core will result in the contraction of the giant star. So once again, the star will become small. Now let us look at the core. The story is going to get very interesting now. The fusion of helium results in the formation of a carbon-oxygen core. It is mainly carbon core with a little admixture of oxygen. Now the carbon core will become degenerate just as the helium core became degenerate because it's even more dense now. And it is inert because to fuse carbon you need a temperature of 500 million Kelvin. So since you don't have that temperature, carbon core will be inert, therefore it will be squeezed and squeezed and squeezed by gravity and will become more and more degenerate. And because it is contracting, the gravitational binding energy release will be much more than when the helium core contracted, because the gravitational binding energy is gm squared divided by r. The radius of the carbon core is much smaller than the radius of the helium core was. Therefore, the gravitational binding energy release, gm squared by r, is even much larger. Therefore, the star will expand once again, but this time it will become a supergiant star. So let's try to understand what it is. What we have right at the center is a degenerate carbon core with a little bit of oxygen mixed in it. That's over there. Its radius is only the radius of the Earth now. Helium is burning just outside, and hydrogen is burning further out, and then you have the rest of the inert hydrogen, which is now very, very large envelope. The star has expanded to a radius of 300 solar radius. The Earth and the inner planets will be completely swallowed by the sun when the sun becomes a red supergiant. And the supergiant will again be convective, just as the red giant star was convective. So now let us look at the full drama using this diagram. So on the main sequence, hydrogen was being converted to helium. After billions of years, the star develops the helium core, which is inert, and therefore it contracts and the star becomes a giant. When the star becomes a giant, the helium core is meanwhile getting hotter by the outside furnace, hydrogen being converted to helium outside. That heat conducts into the core, and therefore helium ignites in the core will expand, and the star will contract. It will come from there to there. And then the star ascends the giant branch once again, and it becomes a red supergiant. In a red supergiant star, you have a inert carbon-oxygen core with some helium still being converted to carbon and some hydrogen still being converted to helium. The rest of the star consists of just hydrogen. So next time you look in the sky, or you look at a star like the Betelgeuse, which is a red supergiant, then isn't it exciting? You know what is happening right at the center of Betelgeuse. You know that it has a degenerate carbon-oxygen core. I think this is absolutely marvelous. So, now this supergiant star at some stage will become pulsationally unstable. It will start vibrating in a periodic fashion. And the amplitude of the vibration will increase, and at some stage it will simply throw out the rest of the envelope. And that's what you see over there. And what you will have is the envelope being ejected just as a snake sheds its skin. And right at the center, you have an inert carbon core, which will cool. And when the fossil heat becomes sufficiently low, KT will once again become much smaller than EF, and the star will become a white dwarf. We shall come to that story in a few lectures. So let's summarize the fate of the lower main sequence stars such as the Sun. For the stars in the lower main sequence, such as the Sun, the story ends there. Where does it end? With the formation of the carbon-oxygen core. The core will never get hot enough to ignite carbon. The core will never reach a temperature of 500 million Kelvin. This is what detailed calculation shows. The envelope of the star is ejected because of a pulsational instability in the star. The core will cool to become a carbon-oxygen white dwarf. Now, let us go back to this diagram and summarize what we have said. So, we had a core, at a certain temperature and density. As the density increased, it remained classical, but finally it becomes quantum mechanical, and then it cools eventually because there is no more nuclear reactions taking place, and then it will settle down in this graveyard as a white dwarf. Now, so let's now continue with the story. So you start with the main sequence star over there. It's a dwarf star. Its radius is only about 1 million kilometers. Then it becomes a red giant when the helium core contracts. And then it becomes a red supergiant when the inert carbon core contracts. And then it ejects the outer envelope of the star as a planetary nebula. And then it eventually leaves behind a star whose radius is only the radius of the Earth, and that is a white dwarf. So that is the story of the star like the Sun. The Sun has not yet finished its story. It's only been burning for 5 billion years. It'll burn for another 5 or 10 billion years before it becomes a white dwarf. How do we know this story is true? Because we see millions and millions of white dwarfs in our galaxy. Here is a classic example of a planetary nebula, and right at the center you see a white dwarf star. That is a carbon-oxygen degenerate star which is not producing any energy. Now that will become a quantum star, and that is the story of Chandrasekhar's great discovery, which we shall come to later. So here are some examples of planetary nebulae. This is the white dwarf, and this is the envelope of the red supergiant that has been ejected. This is a beautiful, beautiful picture. And these are all white dwarfs. Their radii are the radius of the Earth. Their mean density now is 1 million grams per cubic centimeter. And the galaxy is full of these white dwarfs. In the next lecture, we shall pick up the story of the evolution of intermediate mass stars. It is almost similar to the evolution of low mass stars, but there are some subtle differences. We shall come to that in the next lecture. Thank you for your attention.